Hello, everyone. I'm glad to be here with you all in Prague, and especially to be talking about what's really our origin story of sorts to the Magnetite operating system. The journey that we had in porting the first application that we were really working with to what was originally supposed to be on top of seL4 directly. And as part of that journey, we're going to look first at why space is difficult, really, what our initial findings showed about that, how we ended up choosing the initial application to support that we did, and then the process and the lessons learned from actually trying to port it onto seL4 and, well, what became Magnetite. So let's start off with what we actually get from satellite systems. It turns out the answer to that is quite a lot, because we use the products of these systems in terms of data on a day-to-day basis, whether it's communicating with someone across the globe or finding your way around a new city and not getting lost, expecting what the weather is going to be like so you can prepare, or in cases of severe weather like natural disasters, being able to even help evacuate areas. Or in very remote regions, having access to some form of satellite internet, or on more mobile areas like, while you're on a plane. However, with all of that potential, also comes interest from adversaries who consider these satellite systems to be very valuable targets. Salt Typhoon came up earlier. Thank you, Boyd. That's one example. They've targeted Viasat, the satellite internet service. That's only one of several, and all of these are examples, just really a sampling of ones that have happened over the past 2 years. We have an example of GPS jamming that caused a tanker collision at sea. That's dangerous. There's targeting from state-level adversaries for Starlink, the commercial constellation. You name it. And then there's even the rise of focus on satellite security at the Las Vegas conference, DEF CON. So there's definitely interest in satellite systems in terms of security. Unfortunately, the general focus of research in this space isn't so much on how we can actually secure the onboard computer. A good portion of it has to do with things like, are we using strong encryption so we can encrypt our messages? Are we making sure that we have proper controls at the ground station? So we know that people are signed in and vetted when they're sending commands up to the satellite. Are our satellite signals being our sensor signals rather being manipulated, so that we know we don't accidentally turn out of the sun and lose power. However, when we look at the onboard computer perspective, there's a whole host of likely software vulnerabilities because we're running code that, at the end of the day, isn't formally verified, and a lot of it that's developed by third parties, multiple third parties. So what you need is a common resilient foundation at the lowest levels of software to be able to support the flight software above. The applications shouldn't be beholden in terms of full correctness to, let's say, the operating system underneath it, like it would with a monolithic operating system that has been compromised. So we did an initial study, a survey of sorts, to explore the core elements of satellite design, particularly for the software, trying to figure out where the gaps were and where the core pieces were if we wanted to aim for resilience and recovery. And what we found is that, sure, you need a secure foundation, but you really need to go about this in a systematic way. And in the process of this initial research, we identified several significant factors that made survival in space challenging. First off, space is a very inaccessible operational location. When was the last time that any of you went into space to press the reset button on something? Probably never. It's tremendously difficult to do the equivalent of that. Not to mention that, as well as being inaccessible, it's a very hostile environment. You have radiation that could cause bit flips and unexpected behavior for your programs, and it's completely non-deterministic. And what you've launched into space often has swap, or size, weight, and power limitations, meaning that you can only cram so much into that rocket that launched them in the first place, and so you really have to pare down on what you have available on board. And it has to be shared between your core software and the applications running on top of it. There's also a large variety of the kinds of missions that are supported, looking at the use cases that we just mentioned. And so as a result, you get a high level of hardware diversity. And in order to meet it, you get a lot of custom and complex software that are very paired and tightly coupled with it. And then, of course, there's the stress of actually yeeting it into space with a rocket. Not much more to say on that one. Now, let's say your satellite is in space. Everything's going great. You want to hear from your satellite. You probably have intermittent communication access with it, unless it's really high up in space, because it's actually orbiting. So you know you'll be able to get access to it on a certain cadence, but it's not going to be constant. Then you have the need to downlink your information and uplink the right kinds of, let's say, commands for mission purposes. You need some very specialized user training to support that, whether it be to actually send things off to the science team or to just be able to send the right commands to keep your satellite functioning. And then, as if all of that wasn't particularly difficult, a lot of the time, satellites, because they're not in constant access with their owners on Earth, need to be able to operate unattended. So if anything were to go wrong, they need to be able to keep collecting that nice, sweet science data so that it can send it down the next time it actually gets access to its intended ground station. So what we're going to focus on here is how we can help in terms of the custom software angle and how we actually are building up the kind of resilience that the software needs. We're not going to be able to fix any of the hardware issues here, but that's just to say this is the system, this is the environment that these systems are really running in. So in case you didn't know what conference we're at by now, seL4, spoiler, is one of the technologies that we chose to build a secure foundation upon. Ultimately, what we built a set of independent system services to support the space application that we chose, called NASA's CFS. Now, CFS stands for Core Flight System, and if you look at our architecture here, for hardware, we selected the Xilinx Sync 702, very common for space and space equivalent kind of hardware, a little bit old, but this was back in 2018. seL4 on top of that, and then a set of initial services that ended up becoming the version 1.0 of what we call Magnetite, our operating system. So now that we've motivated why it's particularly difficult to survive in space and why it matters, let's look at the application we chose, and then we'll explore the porting process, how it actually all turned out, and the lessons learned. So it turns out that flight software has quite a lot to handle. It's really the real-time brain that controls your mission operations. You can sort of think of it as an autonomous nervous system. I'm probably mispronouncing that, but the idea that it kind of keeps you breathing without thinking about it. And that's really what this is doing here. It helps you communicate with the ground, make sure you're handling data, downlinking that properly, taking in commands right, pointing your system just so that you get the right amount of sunlight, navigating and being able to guide accordingly to see whatever your targets are. Maybe you're tracking the stars and constellations, and making sure that your sensors have the right range of data and that, let's say, your satellite's not getting too hot or too cold, that kind of thing in space. So NASA's Core Flight System, or CFS, is a widely used flight software framework and application suite. The application suite part is kind of novel. NASA CFS is an open source choice that's been used quite a lot across academic research, universities and the like, but also government use. It's originally developed by NASA and is still being developed. It was intentionally architected so that it would be a more reusable application layer than what you might traditionally have to provide a lot of those core functions that we just looked at. Now, NASA CFS wasn't always around. In as late as really the early aughts, there was this clone and own software development mentality. The idea that you would take software that worked the last time, for your purposes. You would fork it or clone it. You would make some changes, maybe not understand all of it, and say, all right, we've run a lot of rigorous stress testing in terms of the physics of it. It's going to suit our purpose. Let's launch this. And around the 2005 timeframe, NASA ran into an interesting conundrum, which was that they were charged with developing 2 large systems simultaneously, SDO and LRO here, acronyms at the bottom, and they only had one software development team to be able to actually create the software to support it. They couldn't split them up, and they needed to be able to support both missions, ideally. So what they did was they stepped back from those specific systems and looked at what common features there were, what worked well, what they could actually make for a more flexible design. And out of that, they created the Core Flight Executive, or CFE. You can think of it as kind of like the heart or the core component of the larger CFS framework. And over the next few years, they developed a series of applications, eventually outsourcing both of those parts. Now, across the subsequent decade after that initial creation, it's been used on a whole host of applications, from lunar, weather purposes, solar observation, to the point that now it's been used on more than 40 different projects. And I say projects loosely. Some of these have, sub-teams and sub-efforts in them. From things that vary as widely as physical landers to spacesuits to satellites. It's a pretty wide range of hardware that this is running on. So how did they actually design it so that they could support this range of different hardware? Well, they designed it such that they have these CFS and CFE applications on the topmost layer. These are kind of your modular, composable pieces that you choose based on your mission needs. These would be running on top of your core layer that contains the most common elements that you're going to need, and basically kind of serves as the glue to bring it all together. And then underneath that, you have your abstraction layer. That's your portability layer. It's what allows you to account for varied hardware, the needs of operating systems, and because of that, it means that when we began our porting effort, we really only had to change what was in this abstraction layer, because everything on top of it didn't have specific system calls. That was all specifically designed to be hosted within this layer. Now, before I go into our process of porting, I'm going to talk about a couple design observations, and some of these will come back around. One of which is to say that, surprisingly, when we looked at CFS, it didn't use heap memory, meaning you weren't going to see mallocs and frees in it. You were going to see, instead, a whole host of global variables to represent that information. That comes with its own consequences, but it's not too uncommon in real-time applications where you need to have predictable behavior, and you don't want to rely on heap memory for that. As well, CFS is designed such that everything is actually in one address space with many threads, and each application is one or more of those threads. So you have an extensive use of memory spaces that are then intended to share information between threads as they communicate. And then the applications themselves are pretty dynamic. They can start, stop, new ones can be added, old ones removed during runtime, depending on what the status of your mission is. And that was something that was pretty unexpected, and we'll circle back to that one later. And then lastly, availability turned up as really the overarching priority in design, because you want to make sure that at the end of the day, your satellite is there when you need it. So you have mutexes, for example, in design that are re-entrant. You need to be able to relock the same thing if you're already the owner of it. It saves time on checking. It's an optimization. Also, more generally, your operations have timeouts. You're not going to be waiting on something that won't arrive if you have a real-time system need at the end of the day for it. So with that in mind, let's turn to the process of porting CFS to seL4. And then we'll do an evaluation of what we got out of that process. Looking at CFS at a slightly deeper level, we poked at the OSAL, or the abstraction layer. We found that, as perhaps expected, it did ease the porting process because we only needed to really change things in one place. But we found that there was actually a lot there. Specifically, there were around 100 distinct API calls. And the functionality that encompassed ranged from message queues, timers, one-shot and recurrent, synchronization primitives like semaphores and mutexes, quite a lot of those. A file system, be able to save and load information, networking, handling interrupts and fault recovery, and also being able to do debug. Now, that's quite a lot of functionality to ask from a microkernel. And to be honest, I don't think it would make sense to, because these are not all particularly generalized features. But what it does mean is that we needed to build a lot of this up around seL4. Now, when we tried to do so, we ran into an issue we didn't expect, which was that CFS is surprisingly dynamic. If you think about it from the perspective of the life cycle of the satellite, what you want running during initial launch versus when it's stable versus when you're decommissioning it might not actually be the same. Or if you're on a lander, the landing period is a very, physically traumatic experience for the system, but it's also a very different period of time than if it's actively collecting data on, let's say, the moon. So being able to actually change up what applications you're running is pretty important. And that means that the resources that go into supporting those applications are also very variable. The synchronization primitives you have to get a lock on the system, the memory you're using, the timers, all those operating system primitives will also change as you're swapping out these applications. A lot of the prior work on seL4 assumes that you have a static resource allocation model. And there's actually very strong reasons for wanting to do that. You can actually get a more well-reasoned sense about the system and its behavior and inherit quite a good amount of guarantees. I won't wax poetical too long about the benefits of this, but there's a lot of effort going on into MicroKit, for example, and it makes a lot of sense. Unfortunately, for this application, it expects something really dynamic, which means just at the fundamental level of how it handles resources, it wasn't a very effective match. And we were working in 2018 or so it was pretty early on. There wasn't much in the way of support for this. So our initial solution was to just essentially figure out what CFS used at a point in time, try to find an ish upper bound that meant it would have enough resources and wouldn't crash, and say, all right, this will do. We basically have given you a ceiling. It's not great for a long-term solution, and so eventually, we actually ended up creating our own approach to support a dynamic creation of resources down the line. But for our initial pass at things, we pretty much just instrumented it to figure out what we should give it in the moment. And when we did that first pass, we built on top of CamKeys, which was what was available to us at the time, and unverified seL4 C libraries. We hard-coded the applications that we're running, so again, we're not doing any kind of dynamic startup of applications. That would make things pretty impossible at that point. And we stubbed out the operating system abstraction layer where possible for those different APIs. What wasn't required, we didn't implement. What was required, we leaned very heavily on existing C libraries for. This is, our proof of concept. And we found particular difficulty with these semaphores and mutexes, your synchronization primitives, because those are one of the most commonly used resources and were often relocked, and you just really had to look quite a lot through the code base to get a good handle on those compared to some of the other resources. So overall, between the difficulty of resource management and the unfortunate lack of dynamism of CamKeys at the time, we really needed an actual operating system, a set of full-fledged system services to support the application, CFS. So what we did was we took all of those API calls, we organized them by the type of primitive that they were reliant upon, and then we bundled those primitives into different services. The idea being that if they have kind of a common set of functionality, they would be in a service together. We also made changes to the board support package because, you're going to have to adapt that for every hardware you have. So in the end, we ended up with 8 initial applications that became ultimately what we called Magnetite version 1, and that would be able to support NASA's core flight system. There were 3 principles that we tried to follow when we developed this, knowing that it could mature down the line, and it very much has since. One was to decentralize responsibility, meaning that we wanted to try to distribute the capabilities at a granular level as possible, which meant that the services, for example, would be their own processes, would own their own capabilities, same with user applications. And the principle of least privilege was also a core tenet, meaning These services were designed on minimal functionality and weren't given any more resources or access than they would need. And then lastly, of course, we wanted to bring in a strong foundation and be able to grow from it. So we turned to seL4. So our timeline has actually spanned several years. We started in 2018 with that initial survey. We began our real proof of concept around the 2019 timeframe, and it wasn't until around mid-2021 that we were able to first run that NASA CFS demo. So there's quite an amount of time in between that I just want to foot stomp that there was a good amount of development required, and the startup did take a good amount of time. That led to our release of version 1 of Magnetite, and then ultimately we've worked our way up to, at this point, version 9. Over the course of that time, we've developed a series of services, increasingly maturing it so that it's full-fledged to support what applications would expect. And in the process, we've also added on support for a series of different platforms. Most of them are ARM because that's just kind of what the trade space is at this point, but we do have one x86 and one RISC-V in there. So how does this hold up compared to, say, real-time patch Linux, which is what we started by, looking at when we first, launched this effort? It turns out that it holds up pretty well. When it comes to things like context switching and round-trip IPC, which fortunately we inherit the benefits of from seL4, it is a very strong contender. One interesting case I'll call out, for sake of time, I won't cover all of these, is mutexes. You might notice that on the left-hand side, it's green on the top, red on the bottom, and it's kind of flipped for ours. That is because we chose to emphasize a different path, and that really shows what the system was designed for. That is to say, Linux is going to optimize the uncontended path, but we were looking for real-time embedded systems that needed a sense of what its worst-case performance time was going to be, have a smaller tailing performance, and have a more reliable average. So that is what we optimized for. And you can see that there with the better worst-case performance and better average, even though our uncontended case might be higher, but it was more reliable. And this isn't to say these are our final numbers as of now. It reflects approximately version 1 and version 2. So we've continued to try to mature and improve that over time. Now we'll look at lessons learned and then wrap up. So one of the big takeaways from this effort that surprised us is that space flight software is surprisingly dynamic. We didn't think about all of the different swapping out that they would want. And because of that, we had to face the question of how to effectively find the system resource maximum. Because if you're changing your system configuration and therefore your resources, what do you do if you only have a static solution? Do you make many system images, treat it like a state machine, and just upload a new image for each one of those states? You could, but it's a lot of effort. You don't usually have a lot of bandwidth to send to some of these satellites. And updates are really tricky in space because if you get them wrong, they turn into a brick. So generally, it sends shivers up someone's spine if you suggest, well, we'll just update it a lot. Another lesson learned was in minimizing temporal trust, because initially Linux processes, which is how things are often done in monolithic systems, will have privileged system processes that are managing the capabilities. They own them, the user processes are dependent on them. Something goes wrong, you don't really have much recourse. So what we ended up implementing was something called self-contained processes, where the processes will own their own memory and capabilities, and if someone else needs them, it's just borrowed on a short-term basis. So they don't actually need to trust the system services. That sounds great and all, but can you trust the processes? Possibly not. And so that's why we also added on something called escrow processes, which essentially pair one-to-one with each of these user processes and holds their capabilities in escrow. So if you do something that you need to create, let's say, new system resources for, you go through those. And it's only a partial monitor, so it's still performant in the cases that you're not using, let's say, or making new resources. So that allows us to do minimal trust between the system and the applications. And then one last thing, which is to say that there are a lot of classic difficulties associated with distributed systems, And we brought all of those to an operating system as soon as we started putting things into a lot of different little boxes. So we had to deal with the same kind of concerns here in terms of ordering things correctly, making sure data was serialized, things weren't locking or relying on each other, and trying to understand everything that needed to be dependent on each other. I could speak a whole ton to that, but I think I'm near my time. So to look back at where we've been, flight software is a critical piece in bringing satellites to life and ensuring that they actually stay operational during their missions so they can collect the science data that they need. Now, decades of space excursions, unfortunately, rely on very tightly coupled solutions between the software and the hardware, meaning they're not very reusable. However, with space being an increasingly, and I say accessible in terms of like cost, operating environment, we increasingly rely on it for a lot of different day-to-day purposes, which means that flight software actually needs a secure foundation because it's receiving increasing attention by hackers. Now, CFS, which is one of the more modularly designed flight software solutions, was what we ended up going for in terms of porting to CFS for a solid foundation, exploring what would be possible. And through this process, which led to the ultimate creation of our Magnetite operating system, we learned a lot of lessons about how surprisingly dynamic space applications are, that you really need to re-architect processes to minimize trust, and that distributed systems problems are just as tough to solve when they're applied to operating systems. Thank you, and any questions?
As you were going through this activity, did you ever find yourself wishing that you could redesign CFS itself? Because if I'm, based on what little I know, that's very, very heavily event-driven, which is harder to predict for a lot of these critical real-time applications.
Yeah, so to repeat the question, did you ever want to redesign CFS during this process? Because it's very event-driven, and that's not particularly static. It's an excellent question. We wanted to work with flight software that was widely in use as it was to see how we could actually build up security for it, because this is used across academic spaces, it's used across government spaces, and so it was very realistic in terms of a target to try to build up a secure foundation for. Have we actually explored what flight software could look like? Yeah, we've done a look into that, but I would say for our initial purposes, we were looking at what would be lower than the application layer.
Thanks for the nice talk. I was just surprised that you compare CFS on top of seL4 with CFS on top of real-time Linux, which I would not consider a gold standard in real-time domain. So how does it compare to, let's say, a more mature real-time operating system, Artemis, for example?
So we were comparing it to the basis of real-time patch Linux because that's what a good portion of actual space systems use. I mean, if you think you shouldn't be flying Linux in space, I might agree with you, but it is done, and it is not uncommon. So we wanted to have it compared to a baseline that was practical for what was being used out there. Artemis is also used, you're right. In terms of what we could get access to, but also what we saw as practical for the purposes of our initial community that we usually operate within, that it just kind of made sense to stick with that one. So I don't have other particular comparison values for you, unfortunately. I will say, though, it doesn't compare directly to seL4, it compares to Magnetite. So there are layers that add extra cost of time.
So just a quick question on the ecosystem for seL4 as it stands right now. Like I know you mentioned CFS has like 100 or however many API calls that it abstracts. Like of those, how many did you find like within the open source community for seL4?
I'll repeat your question and then probably ask for a bit of clarification. So when looking at seL4, or when looking at CFS, how many of those API calls did you find within seL4? So I believe you're asking what calls from seL4 we were able to use directly in satisfying those APIs?
I guess sort of community contributed software that provides this functionality?
Sure. So in our case, we ultimately relied on existing C libraries for the few that we saw were the most critical. I would say there was a small percentage that we were able to actually provide support for while stubbing out the rest and keeping it minimally functional for things like housekeeping. And we did pull from what was existing in the community in terms of, you know, popular C libraries and the seL4 community for those. But really for that first pass, we were trying to keep it as minimal as we could just for proof of concept purposes. A lot of it we did have to end up stubbing out because there wasn't a direct one-to-one.
Any other questions? Gary?
How good are the chances look that this will fly on a mission?
Fingers crossed. I am very much enthused about the prospect, and we are working on that. It's pretty mature at this point. That really is up to there being a willing partner out there who would have a space launch, because space is very much about heritage, and if it hasn't been up there for about 15 to 20 years, it's a real risk, again, with the bricking your satellite. So yeah, we would love to have a partner who would help us to launch that. It's just a risk question. And with that.
Okay, thank you very much.